We'd been searching for an interesting problem until we saw that pile of spheres. Then we started imagining what dimensions beyond the real world might look like, and felt just how hard it was. But from that moment on, it felt like we had the power to create a new digital life.
In three-dimensional space, you can imagine a pomegranate. It's like a polyhedron with seeds packed inside. If you replace the seeds with spheres, how many unit spheres can touch the central one? That's the kissing number problem Newton proposed over 300 years ago.
Newton thought there should be 12 spheres, while Gregory thought 13. He noticed that the spheres weren't completely locked in. There was still some room to move. In 1900, Hilbert officially presented 23 problems at the International Congress of Mathematicians in Paris, which guided major directions in later math research. One of the key points of the 18th problem is the kissing number problem.
This problem is actually very simple to state, yet incredibly deep with important practical applications. In information coding, you want to compress the most information using the fewest bits, and that's closely related to the sphere packing problem.
Once you get to 4, 5, or 6 dimensions, it goes beyond human intuition. In the past 50 years, there have been only about 7 major breakthroughs, all by mathematicians, each using very unique and completely different methods. In higher dimensions, even the best mathematicians feel completely stuck.
When we talked about the 2022 Fields Medal and the breakthroughs mathematicians made on the sphere packing problem in certain special dimensions, we started thinking beyond the mathematicians' advances from a purely mathematical perspective. Could we bring our team's earlier successes in multi-agent learning and reinforcement learning into math to actually give humans new insights and discoveries in fundamental mathematics?
Mathematical problems don't come with tons of training data, which is completely different from using large datasets of known protein structures to train AI to predict new ones. In a way, it's a process of creating something out of nothing.
We needed to make sure of two things. The spheres don't touch each other, and we have as many spheres as possible. In the first approach, I made sure they didn't touch and then tried adding spheres little by little. In the second, I focused on packing in as many spheres as possible first, and then adjusted them so they didn't touch.
At first, I was looking for patterns in some of the existing lower bound structures. Back then, the main approaches were based on lattices and on error-correcting codes.
We took a different approach from the mathematicians. Starting from the basic constraints, we just asked where the next sphere could go, turning a fill-in-the-blank into a multiple-choice problem.
At first, we couldn't even handle 4 dimensions, and then suddenly everything below 8 dimensions was solved. But we quickly realized that no matter how much we optimized the method, there were some limitations we just couldn't overcome, like issues with numerical precision.
As we added more spheres, numerical errors kept piling up, eventually becoming big enough to mess up the entire packing.
We got stuck around 8 and 9 dimensions. Beyond that, there was simply no way to make any progress.
On a sphere, if you have 2 points, you can draw a line between them through the origin and compute the cosine of the angle between them. These cosine values aren't random, they actually come from a finite set. So instead of just turning the whole coordinate space into a discrete multiple-choice problem, we could turn each cosine value into a choice too. This makes the options much smaller, and the whole picture much clearer and more elegant.
For example, in 4 and 24 dimensions, the cosine values are extremely regular. They converge to just a few specific values, so instead of searching directly in coordinate space, we shifted our approach to filling in the cosine matrix.
The cosine matrix only cares about the positions between spheres, turning a really complex high-dimensional geometry problem into an algebra problem that's much easier for computers and AI to tackle.
With this formulation, all computations are transformed into parallel operations on matrices, introducing almost no numerical errors. It naturally fits the logic of large-scale GPU computing, fully unleashing the potential of AI models and making high-dimensional problems manageable.
We still needed the most efficient learning algorithm, so we framed it as a game and used reinforcement learning to train an agent to play it. At each step, the agent picks an entry from the available actions to fill the matrix. The game ends when the matrix can't be filled any further. and we reward the agent based on how big the matrix has grown.
We realize this problem is perfectly suited for reinforcement learning because RL is all about figuring out how to learn an optimal set of strategies in a high-dimensional space to maximize a reward function.
On the other hand, adding spheres isn't like playing Go. The order doesn't really matter. Adding an ABC order or BCA order gives the same structure. We need to avoid repeatedly exploring the same paths, so we batch remove geometrically equivalent options from the huge set of candidates. Otherwise, it hurts the diversity of trajectories and slows down learning, making it hard for the AI to develop a good strategy. Sometimes, we don't add entries one by one. In certain cases, we allow multiple entries to be added at once. This greatly improves trajectory distribution and speeds up trial and error when the AI interacts with the environment, letting us efficiently control how finely we add spheres.
I think intelligence should emerge through constant interaction with the environment, trying again and again, and gradually getting better. It's actually very similar to how animals in nature learn new skills.
The results were stunning. What used to take tens of hours in 8 or 9 dimensions could now be done in just a few tens of minutes. But after running for a while, we hit a wall around 15 or 16 dimensions, and the program just couldn't run.
In the past, humans relied on a spark of inspiration to discover new things, new structures, new scientific laws. Now, with AI and science having reached this point, the question is, what can AI actually do? My goal is to use AI's engineered stability and efficiency to offset the uncertainty of scientific discovery and speed up mathematical breakthroughs. Having a strong engineering team working together to understand the problem and optimize it is a really crucial step. Computation and intelligence are inseparable. If I have a method that can quickly search through all the answers, I'm basically the smartest person. And if I can speed up the search by several times, something that used to take 3 years could now be done in just 1.
At the beginning, we were just calling some native CUDA operators, but we realized that a huge amount of time was being wasted moving data from the GPU back to the CPU. So we decided to redesign the operators ourselves, making everything read and write directly on the GPU. With this new setup, we get about a 2.5 speed up.
We also optimized communication volume, compressing data transfers. We could also adjust when synchronization happened.
Some operations in the computation require very high precision, while others don't. We designed a mixed precision system to push each operation to its precision limit, which greatly boosted efficiency. We also pre-cached key information, so afterward we could quickly query and schedule with minimal computation.
This optimization was actually straightforward. Every few hours, we saved the current state, so if any machine dropped offline, we could just reload the latest checkpoint and keep going from there. We not only improved the efficiency, but also made it possible to scale up the overall compute much more reliably.
We worked with the engineers to turn all the 4 loops into parallel operations, which massively improved efficiency. Gradually, the program could scale to 15-20, even over 30 dimensions.
If the cluster crashes in the middle of a run, no matter how fast it is, you'll just fail and restart. So we did engineering optimizations to enable deeper, uninterrupted searches. On a large scale, every engineering improvement is essentially a speed up.
But as we ran more experiments, we realized that even though the scalability had improved, we still couldn't get the desired results in practice.
The most difficult problem we faced back then was 14 dimensions. We just couldn't reproduce 1932.
After thousands, even tens of thousands of experiments, every single one failed. That 1932 in 14 dimensions became like a nightmare, haunting us for more than half a year. I even had dreams about getting 1700 something NG, but they were all illusions. It was the only known result by mathematicians that we couldn't reproduce. If we couldn't reach 1932, it would mean our AI still had some fatal flaws.
I often asked the Qingdong whether we had reproduced the known results, whether we had broken the lower bound. Despite the pressure, this work is incredibly valuable and worth the effort. It has high mathematical significance, and these explorations also inspire new AI techniques, especially in search and reasoning. That's why I think a team like this should tackle it together.
Changdong's way of thinking is very different from those of us in the math department. His intuition feels strange to me sometimes, but it's definitely complementary. In the end, to reproduce 1932 in 14 dimensions, I had to manually remove a few spheres, and it worked. Humans can do that kind of adjustment instinctively. At that time, the machine couldn't.
Sometimes a single sphere is like a mouse harms a pot of soup. Once you add it, the entire structure falls apart. So we started asking, can we build a correction mechanism to spot these bad spheres? In other words, use another agent to simulate the kind of manual fixes a human would make.
These two agents need to cooperate, using a game-theoretic approach to solve a very complex high-dimensional optimization problem. The cleverest part of this work is that Chengdong turned the kissing number problem into a game, and this game can be solved with reinforcement learning.
The second player basically adds a regularizing constraint to the originally huge and chaotic high-dimensional space, significantly shrinking the search space and greatly improving our reinforcement learning system's efficiency in value estimation and strategy optimization. We quickly put this idea into practice and immediately reached 1932 in 14 dimensions. At that point, our AI system could fully reproduce all the existing results.
The lower bound is basically just reproducing or reaching the best known results. What we're after is pushing beyond the known limits, discovering something completely new that wasn't there before.
At that time, we prayed when we saw objects with spheres, trying to see if they could add a sphere to the structure for our algorithm.
The unknown thing we're exploring is, in a way, nature itself. In game theory, there's also something called nature. It's what designs the structure to have this naturally explosive complexity. What we have to do is find the path through the maze that nature has created in this huge space.
We were walking along the riverside in Shuhui, Shanghai, looking out over the water. We just had this feeling that one day we were definitely going to make it happen. And that day felt closer and closer.
Because our project was already pretty unconventional, I wanted to spark some interdisciplinary interactions. So I put a note on the fridge, free cocktails for everyone. After entertaining all my friends, I stayed behind alone to clean up the bar. That's when the real inspiration came. Completely different ideas started flowing in, and all sorts of weird, unexpected thoughts popped up. We found that after breaking down the structures generated by the AI, lots of substructures with good geometric properties appeared. We call these substructures fragments.
Every time the agent finishes a round of the matrix filling game, we break the matrix into geometric fragments of various sizes and try to reorganize and keep filling them. The whole process feels like cells constantly dividing, generating more and more new digital life. In over 200 experiments, a really strange fragment suddenly appeared. When we tried to fill it further, it seemed to create something completely different. I had to rewrite some code to verify it, and my mind went blank. I kept typing mistakes over and over.
We ignore the diagonal entries and making sure every value is less than or equal to 0.5. Then we compute its rank and check whether it's 25. Finally, we estimate what the largest cosine value could be.
We were so excited, truly over the moon. We finally broke through the lower bound.
It felt a bit like trying to shoot an arrow to the moon. That's the charm of the problem. You never know if the arrow will come back until you actually shoot it. Everyone said our project was doomed, but luckily, we made it. At that moment, it felt like the arrow had broken through something, like reaching the first or second cosmic velocity, and it really hit the moon. The feeling was just incredible.
It's like that legendary move in AlphaGo. When I watched it live, all the commentators said it was a mistake, but in reality, it turned out to be a brilliant move.
Of course, my goal was to break a lower bound by hand. In a way, I was competing with the machines inside our own team. If I couldn't do it, but the machine could, then it really meant the machine had done something beyond what a mathematician could manage. And in the end, it was clear, breaking that lower bound was simply not something I could have pulled off on my own.
Later, we started finding more and more counterintuitive phenomena. In some structures, there wasn't a single pair of antipodal spheres. yet the symmetry was still incredibly high. Even more fascinating, it was like building gravitational channels in the universe, connecting geometric isolated galaxies that were scattered across different dimensions. It let us and the mathematicians understand the problem from a bigger, more systematic perspective.
I think the thing I spent the most time on was trying to interpret the data coming out of this AI black box. There's a great word in English for what I was doing, exegesis in ancient Greek. It meant interpreting an oracle. The AI, like a black box, tells you, I've done better than humans, better than all previous results. But the real question is, how do we interpret that? How do we make sense of the insight it's giving us?
I think this work is really cool. It was actually done by just 6 very young students, combining fundamental disciplines with AI. I really feel that Chinese scholars, especially this younger generation of researchers, are incredibly talented.
The role AI plays in this process is to help young scientists explore the unknown more efficiently. In itself, that's a kind of romance, humans and machines exploring science together.
Over the past year, every day was all about algorithms, structures, and numbers, wrestling with them. The path felt dark and endless, but once we finally broke through, it was like the world lit up, as if a vast new starry sky was waiting for us. Packing Star became the spaceship carrying us to explore that sky. And this isn't the destination. It's a whole new beginning.